Welcome to part 2 of Ogerudi's electromagnetic consciousness theory. Electromagnetic consciousness, a mathematical framework for brain functional non-locality. This introductory slide presents the abstract and lays out the conceptual foundation. The key idea is that electromagnetic activity in the brain must be described as field tensors evolving within a curved, heterogeneous, and anisotropic Riemannian manifold, the real geometry of brain tissue. The formulation integrates all known contributors to the brain's electromagnetic activity, action potentials, ionic currents, biophoton emissions, and local field potentials. These diverse sources combine into one unified mathematical object, the tensor F mu, which interacts with the curvature of brain tissue to create structured interference patterns. These interference patterns are not secondary phenomena. In this framework, they are proposed as the physical basis of functional non-locality, providing a mechanism by which distant brain regions can coordinate through coherent electromagnetic propagation. This is the first framework to explicitly define consciousness-relevant EM fields through geometry-grounded tensor equations. This slide introduces the central equation of the model. F mu equals mu J nu. Here, F mu is the electromagnetic field tensor, and J nu is the total current density. Ogerudi places this formulation inside the curved manifold of the human brain, meaning that field propagation is shaped by local tissue curvature, anisotropy, and conductivity. This formulation integrates classical ionic currents with ultraweak biophoton emissions, treating them as components of the total current vector. Thus, quantum-level photon emission and macroscopic electric currents are mathematically unified. The slide emphasizes that interference and resonance must be solved within this curved geometry, not in flat Euclidean space. The curvature determines how EM waves evolve, focus, and overlap. This slide establishes the precise mathematical foundation that allows later slides to describe interference, hotspots, and non-local propagation in a formally consistent way. This slide visualizes how the total electromagnetic field tensor produces complex interference patterns inside the brain. We watch 4 conceptual stages. A. Individual sources generate waves. B. These waves superpose, forming interference fields. C. Hotspots emerge where constructive interference intensifies. D. Functional non-locality appears as changes in one region ripple into distant regions through the field. Mathematically, each component of the field has an amplitude AI, x, and a phase phi I, x, t. Their superposition creates hotspots, high-intensity nodes that can influence neural firing thresholds. The novelty here is profound. Ogerudi proposes that the structure of these interference patterns is a computational substrate. Hotspots act as amplification nodes, routing signals, binding information, and enabling long-range synchronization not dependent solely on synaptic wiring. Previous theories talked about field effects. This is the first time someone offers a full tensor-level, geometry-aware, interference-based mechanism for functional non-locality in the human brain. This slide expands on the time evolution of interference within the brain. The interference landscape is dynamic. Hotspots emerge, drift, merge, and decay as neural activity changes. CSF boundaries reflect EM waves, cortical curvature bends them, and tissue heterogeneity shapes their coherence. Ogerudi demonstrates the first dynamic EM field model that couples interference to neural excitations. Hotspots trigger new neural currents which generate new EM fields which reshape interference, and the cycle continues. This establishes a self-updating, nonlinear, feedback-driven EM ecology inside the skull. No prior EM consciousness model provides this dynamic, mathematically grounded mechanism. This slide links the electromagnetic formulation directly to cognition and brain function. Here we see how interference patterns correlate with activity in real neural systems. Wernicke's and Broca's regions during linguistic processing. Medial temporal lobe during multimodal memory integration. Prefrontal cortex during decision-making. These regions generate EM patterns whose interactions, not just their synaptic wiring, contribute to unified perception, language, and higher cognition. Ogerudi argues that functional integration emerges from coherent EM interference, complementing and sometimes surpassing what synaptic connectivity alone can achieve. This is the first theory that provides a mathematical electromagnetic explanation for why distributed brain regions synchronize during complex cognitive tasks. This slide visualizes one of the most important outcomes of the model: the formation of canonical focal points, where information converges electromagnetically. The slide sequence shows: A. Initial sensory focal points, visual, auditory, somatosensory. B. Formation of a primary canonical focal point at Wernicke's area. C. Emergence of a secondary canonical focal point at Broca's area. D. Coherent EM correlation between Wernicke and Broca. These focal points are not anatomical structures, they are constructive interference nodes predicted by equations. They act as computational hubs, concentrating EM energy, binding multimodal information, and routing signals across distant cortical regions. This mechanism explains rapid, flexible cognitive integration. The EM field dynamically reorganizes itself, creating new focal points as needed, without requiring new synapses. The EM model that mathematically defines and predicts field-generated cognitive attractors. Part 2 concludes with a unified view. Ogerudy presents the first complete mathematical framework linking EM tensors in curved anatomical geometry, neural currents and biophoton emissions, interference dynamics, hotspot-induced neural modulation, canonical focal points, and field-driven information flow. Together, these form a coherent architecture where cognition and consciousness arise from structured electromagnetic computation. Future directions are bold and testable. Full 3D FDTD simulations on brain geometry. MEG/EEG detection of predicted EM focal points. Non-invasive field perturbation experiments. And EM-inspired artificial intelligence architectures. Ogerudy's Part 2 transforms the theory from an idea into a predictive, mathematically grounded scientific model. This is the frontier of electromagnetic consciousness research. The rest slides contain the full text of his paper, and this final slide lists the complete reference set grounding the theory. These include works on electromagnetic field propagation, consciousness theories, MEG/EEG physics, quantum biophoton studies, traveling waves, CSF dynamics, metamaterials, and nonlinear neural oscillators.